This is lecture 5 of Machine Learning and Bayesian Inference. In the last lecture, I talked mostly about the Bayes optimal classifier and about how you can use that idea to talk about how you might optimally go about the process of doing supervised learning from data. And that showed up a really important idea, which is that ultimately you should be averaging over all possible functions that map your feature vectors to your class or to your real number in the case of regression, rather than just trying to pick one of them. I'm going to put that on the side for now. I'll come back to it later and talk about how you actually try to do that in practice, even though it's very often, in fact, intractable to do so. And I'm going to return to the possibly more familiar scenario where you're doing supervised learning, but you're just trying to pick a specific function from your feature vectors to your class or to your real number for regression, depending on the scenario that you're in. And I'm actually going to do that by developing in quite a lot of detail algorithms that are inherently, essentially linear. And there are two reasons for that. Firstly, linear things are generally straightforward. Once you put nonlinearity into stuff, then it starts getting tricky. But it turns out that there's a simple trick that we can play with just a linear classifier or a linear regressor that makes it suitable for application to problems where the data would otherwise make just a linear relationship unsuitable. And the second reason is that if we take that trick to a bit more of an extreme, we end up with the support vector machine. And the support vector machine, as I think I mentioned in possibly the first introductory lecture, is really a state-of-the-art technique in the scenario where you don't have huge quantities of training data, and so deep neural networks, for instance, may not be an appropriate thing to use. So that's what I'm doing today. Now there's a classic example of why purely linear classifiers can fail quite easily for even quite straightforward data sets. What do I mean by a linear classifier? Well, I basically mean just a perceptron. At the end of last year's artificial intelligence course, there were some exercises that were set for you to do as supervision work. Some of those exercises towards the end involved looking at the geometry of a basic linear perceptron. That geometry is important, and it's going to come up quite a lot in this and in subsequent lectures. So, I strongly suggest that you go back and redo those exercises. I'm going to give just a summary now that gives you a way of thinking about what's going on, but this is sufficiently important that it's worth just revisiting it. Anyway, what I'm talking about here is the simplest form of classifier. We've already seen quite a lot of mention of the perceptron, where the underlying relationship looks like this. And where you may be having some kind of activation function, so it's quite possible that this is wrapped up inside an activation function. Now, I'm going to take that activation function off just for now. We can talk about it again in a minute. But the important intuition to have is that, let's put this in 2 dimensions. So we just have the plane with x1 and x2. The solution to the equation that makes this whole thing equal to 0 is then a straight line in the plane. So we will just get a straight line. which corresponds to h sub w of x being 0. The way in which you set the weights then sets where that line is. And in particular, the orientation is shown to you by the direction of the weight vector w, which in this case is just w1 and w2. And the distance here depends both on mod w and on w0. Okay, and you could normalize mod w to be 1, in which case the distance is just w0. But the point is that that weight vector with the non-bias weights, okay, everything except w0, gives you the orientation of this line. And then the weights as a whole tell you how far away it is from the origin. The other important thing to appreciate about this scenario, let's get rid of some of this stuff. Is that on one side of this dividing line, h sub w of x is greater than 0, and on the other side it's less than 0. And you can imagine, in fact, a plane cutting through the x1, x2 plane along the dividing line and being above 0 on one side and less than 0 on the other. And this is how that perceptron ends up being used as a two-class classifier, because we will put an activation function on here, and hw of x then, for example, may output class 1 for one side of the dividing line and class 0 for the other side of the dividing line. Or it may be a sigmoid function and it doesn't give you 1 or 0, but it gives you something positive and tending to 1 on one side and something less than a half and tending to 0 on the other. Okay, but this is the basic geometry of the situation, and that's essentially how a perceptron with a linear function underlying it acts as a two-class classification device. Now, with all that in mind, it should be obvious that using just a perceptron, using just a linear classifier, you could learn to separate the data on the left-hand side of this diagram. Okay, you can happily try and learn some weights which will put your dividing line between these two classes. But that is not the case for the example on the right. This is a classic and old problem, and it essentially killed off neural network research for many, many years until people found a way of getting around it. Now, there are lots of ways of getting around it. Okay, it's no longer regarded as a sticking point in any way whatsoever. But the way I'm going to propose that you can get around this while maintaining a fundamentally linear approach to machine learning is to use something called the kernel trick. And this is remarkably straightforward. The fundamental idea is that you take your original feature vectors and you map them into a space typically of higher dimension. Now, on this slide, I've taken the right-hand graphic from the previous slide and mapped all the examples in it into 3 dimensions rather than 2. And in order to do that, all I've done is added this extra dimension, which is the product of the original 2 dimensions. Okay, so now the z-axis here is the product of x1 and x2. So we've mapped all of that 2-dimensional data from the previous slide into a 3-dimensional space. Now, think about this for a moment. Let's just go back and look at that data. The blue clusters that form one of the classes are centered around the origin and around 1, 1. The other 2 clusters, the red ones, are centered around 0, 1 and 1, 0. If you take the product of x1 and x2, what you're going to tend to do is lift this cluster up in the Z dimension. And you can see that that's precisely what's happened here. Now, if you can visualize that, you should be able to see that a linear classifier working in 3 dimensions now can separate these classes. Instead of having a line in the plane, you now have to visualize a plane cutting between the blue clusters and the red clusters within this 3-dimensional space. And that is something that you can in fact do. In fact, in the next slide, I'll show you that specifically. In fact, I'll do it now because I can come back to the intermediate slide without too much problem. Okay, here I've done this using something called the iterative recursive least squares, or IRLS algorithm, which I'm going to go on to derive for training these things. And hopefully you can see from, well, these are 2 views from different angles of the same solution to the problem. My linear classifier now implements this plane within the 3-dimensional space that has been slid between the 2 classes, now that I've expanded the original 2-dimensional feature vectors into 3 dimensions. Okay, so this is a simple but really rather lovely idea. Take your original data. If you can't separate it linearly, then try to map it into a bigger space that gives you a bit more elbow room, if you like, and allows you to do just that. This is the essence of the kernel trick. Now, what was I going on about with this slide that I just jumped over? Well, a couple of machine learning commandments here. The first is this. This is toy data, okay? It's entirely artificial. Toy data is fantastic for making a point. It's fantastic for illustrating things. It's pretty useful if you've implemented a learning algorithm and you want to make sure it's doing something sensible. But in terms of telling you how your sparkly new learning algorithm might work in the wild when you subject it to real nasty, gnarly, proper data, it's not really any use to you at all. Okay? If you get into the business of deriving new learning algorithms, whether they be supervised or not, you ultimately have to put them to the test of real data sets. Okay, so don't be tempted, just use toy data. There are plenty of real data sets available. This is just one particular place where you can find an extremely large collection of them drawn from all manner of different applied problems. But you should make use of such resources if you actually really want to know how well your method is doing. The second commandment here is I shall not rebrand the kernel trick. The kernel trick has been around for decades. Every now and again someone manages to rediscover it and then quite often gives it a fancy name and tries to present it as something new. This is not a great thing to do because there are plenty of us who've seen it before, and you should really just let it be as it is. It's the kernel trick. No one needs to reinvent it. So, what do we want to do next? Well, we're interested in linear classifiers, so let's firstly set up some notation here, so that we can speak about using this kernel trick in a more formal way, and this is going to be useful. What I have here first is just the definition of a linear classifier with an activation function attached to it. And as I've pointed out on earlier occasions, if I include a special input that always has the value 1, I can write it in a particularly nice form, just like that. In order to introduce the kernel trick, now, the reason it's called the kernel trick will become clear, but not for a little while, okay? So, we'll just... I'll promise to tell you where the word kernel comes in, but that comes later on. We want to do a general version of the trick that I've just shown you mapping our x vectors into a higher dimensional space. And we do that by introducing these guys called basis functions. Phi sub I, okay, there may be several of them, so we index them by the subscript I. Now, the one that I used in the example was just phi of x1 and x2 equals x1, x2. Straightforward. But there are many families, and we'll see more of this later, of specific basis functions that turn out to be more or less useful in practice. Once we've got a bunch of those, we have this mapping denoted by capital Phi that takes one of the original feature vectors and places it into a larger space. Okay, K is typically larger than n being the space that we start off in. And that gives us this equation for our classifier, or our regressor. And as usual, if we have one special basis function, in this case that always maps its vector to 1, then we can again use this trick to write our classifier in a slightly nicer form. Okay, so this is the important point. This is the important equation on this slide. Okay, our classifier, or our regressor, h sub w of x, takes x, does something to it depending on the weights in w, and now it does the same linear thing as before, but first it uses capital Phi to map x into a space of higher dimension. Now we want to know how we're going to train one of these things, and I think I can hear you already suggesting to yourselves that you do it by gradient descent, and yes, you can. Okay, we haven't actually changed an awful lot. We can apply all the earlier arguments about modelling the data probabilistically and then having a maximum likelihood or a maximum a posteriori algorithm. Yes, indeed, we can do all of that, and we can do it by gradient descent exactly as we did before. But actually, there's a much nicer way of doing it. We don't actually need to use gradient descent in this case, and we have some better approaches to training classifiers or regressors in this format. How does that work? Well, okay, let's start with linear regression. Okay, let's just do the regression case. And let's say we want the maximum likelihood algorithm, and we're going to assume Gaussian noise. Well, that means that, as usual, we still want to choose our weights to minimize the sum of the squared errors. Okay, all of that derivation just carries through unchanged. We want to minimize this guy. And previously, sure, we would have done it by finding its derivative with respect to the weights w, which is pretty straightforward, and then taking little steps in the downhill direction. But in this case, and this is fairly rare, we can actually solve this analytically. We can do it directly by just setting the derivative of the error with respect to the weights to 0 and solving the equation. Okay? You want to find a stationary point on a function. This is how you would generally try and do it. Okay, we didn't do it for multi-layer perceptrons because can't solve the equations. That's why you need gradient descent. But now I propose that we can solve these equations. Okay, so that's what we need to take a look at next. Now, at quite a few points in what's coming, we're going to be manipulating expressions involving vectors and matrices. And we're going to want to be able to do things in particular like take partial derivatives. You may find that in order to get the hang of this, you actually have to just take a bit of practice, get yourself some blank paper and a pen, and actually write some of these relationships out in full to convince yourself that they work. Alternatively, if you search a little bit on the web, you will find quite large collections of identities involving matrix calculus that you can use in their own right. But of course, You guys want to know how this works, don't you? I hope you do. So it's worth actually taking the time to convince yourself that this stuff works as advertised. Now, in particular, for what's about to come, you'll find that a lot of the standard things that you remember just from calculus in a single variable carry over in quite a natural way to calculus in several variables when you're depending on vectors and matrices. So there's a simple example here to start with. Okay, what we've got is the derivative of A transpose X with respect to X, where A and X are both vectors. You know, of course, in one dimension, if A is a constant and you differentiate AX, you just get A. Okay, so I think we can cheer at the fact that when you differentiate this vector version, you still end up with A. Okay, and it's straightforward to see that, because you can write the definition of what it means to differentiate a single-valued function. Okay, A transpose X is just something that evaluates to a single number with respect to a vector. Okay, you just differentiate with respect to each element of the vector in turn, and you get a vector as a result. And differentiating in order to get any of these, let's say we take the jth element of this vector here, we write it out in full and it looks like this. And if we're differentiating with respect to the jth x, then we just end up with the jth a. So collecting those together into a vector, we just end up with a again. Okay, now you can do this for the more complex examples as well. And in fact, I'm suggesting here that you should definitely verify for yourself that these things work as advertised. So here's an exercise. I've got a symmetric matrix A. Now, in one dimension, in calculus of a single variable, if you differentiate ax squared, and a is a constant, you get 2ax, yes? Well, luckily, in this case, when a is symmetric, we get essentially the same thing. Because here we're taking a derivative of x transpose ax, which looks pretty much like ax squared, and you can't write ax squared because these are vectors and matrices, but it has the same kind of form, and we end up with the same kind of result. But you have to be careful. If a is not symmetric, the result is slightly different. And if you want to make sure you really know your way around this, try and work out what the equivalent result is when a is not symmetric. Okay? But all of this you can do just by expanding out what it means, for example, to multiply a matrix by a vector, and then applying the usual rules for partial differentiation. Okay? I leave you to do that at your leisure. If we then try and do this for the linear regression case, everything gets carried through in quite a straightforward way. First of all, I form this matrix phi. Okay? Now, in order to get this, each row corresponds to one of the feature vectors in the training set that's been expanded into the bigger dimensional space. Okay? So each row of this guy here is one of my training vectors, but in the bigger space. You can then write the sum of squared errors in this quite nice format. Okay? Why is that? Well, if, for example, I take a product like capital Phi times the weight vector w, okay, what do I get? Well, what I actually end up with is that each row of the resulting vector looks like this. Okay, so these values are, if we look back a little, precisely these values. Okay, computed for the feature vectors in the training set. We're doing regression now, so there's no activation function. What we then have is that y minus this guy is then y minus, I haven't got enough room, okay? I hope you'll forgive me for squishing my notation up a little bit here, is now y minus, well, each of these guys is just the output that our regression model gives for one of the input vectors, and the elements of y are the target values. Okay, so this gives us a vector of the values that tell us the difference between the targets and what we're currently predicting for a given weight vector w. And then this thing taken as a whole, because we are taking an inner product here, this corresponds to the sum of the products of corresponding elements in those two expressions in brackets, and we end up with E of w actually equals the sum of squared differences that we're trying to get hold of. Okay? Just remember that if we take for any vector x, x transpose times x, what we're getting is the sum of the corresponding elements. Okay? So this all works out nicely. Now you can also convince yourself that if you have expressions involving vectors and matrices in this ways, then the usual rules for things like multiplying out brackets work as you would hope. You multiply out the brackets to get this expression, and then if you use, in particular, the expressions from the previous slide on the initial results on how to differentiate expressions of this kind when there are vectors and matrices involved, you can differentiate E of w, the error expression, in order to get this expression here. The final step then is just to set that derivative, dE of w by dw, to 0 and rearrange, and you get this expression. And so by inverting the matrix theta transpose theta, you can analytically solve in order to get the weight vector that minimizes the sum of squared errors. Okay, so that is the maximum likelihood solution for training a linear regressor when you've mapped the original vectors into this bigger space using the basis functions denoted by these phi values. Now there's a slight word of warning here, which is that one has to be careful in practice computing matrix inverses. I'm not going to go into the numerical analysis part of how you might go about this, but you may find that in practice just taking the inverse straight away is not necessarily the best way of doing this. There are numerical issues potentially that can involve you in doing it in a slightly more roundabout fashion. Okay, but the important point is that you can solve this analytically, and with care in the numeric analysis part of finding a solution, you can find W opt quite happily for this particular problem. Now I also spoke about the maximum a posteriori version, which modifies the error function slightly, because now we have this extra term that we need to deal with. It is an exercise in the exercise sheet handout for you to carry through the derivation in this case as well. So this is something that you need to do in preparation for your supervisions, and which you can discuss with your supervisors if necessary. But the outcome should be that now your optimum weight vector is given by this expression. Again, this can be computed numerically without too much pain and suffering. Now this is called regularized linear regression. I've already mentioned the term regularization and tried to impress on you why it's there and why it can be important. You'll also see this method referred to as ridge regression. This is another standard term that's used to cover this case. But I think it's worth just revisiting slightly the importance of this extra parameter lambda when you look at training from this perspective. And in order to do that, I can go back again to my original example and show you the effect that lambda might have. Lambda is something called a hyperparameter, and it turns out that setting these is fantastically important and a really, really critical thing to get right. Let me just recap slightly where that term has come from. Okay, this term was a long time back often introduced informally because people realized that by keeping the length of the weight vector small, the function that they would be learning would be relatively simple, and so you would tend not to overfit because you would be preventing your function from wobbling around so much that it tried to fit the noise in your data. I then introduced it as an extra term for the maximum a posteriori approach to deriving learning algorithms, and it turns up because you put a Gaussian distributed prior distribution on the weight vector, which again is leading you to prefer weight vectors that have a small length. Okay, you want mod w to be small. The important point here is that there is now this hyperparameter lambda. Now, if you set that to be a large quantity, it's having a big effect on the error, and long weight vectors will increase the error disproportionately. If you make lambda 0, you go back to the maximum likelihood version of the algorithm. If you make lambda small, you will be trying to force the algorithm to use small, not too long weight vectors, but you won't be imposing that too hard. Where you actually draw that trade-off turns out to be pretty critical. So here, by way of illustration, I've gone back to my original problem, and you can see here that the maximum likelihood solution is not particularly good. Okay, it's trying quite hard to fit the noise, and the solution, the yellow line, is not giving you a good approximation to the actual underlying relationship. However, as I gradually increase lambda across these diagrams, you see that in particular around here and around here, we're getting a much closer approximation to the correct relationship. But then as we impose this regularization more strongly for the last two, we're constraining too much the kinds of function that we might consider, because we're forcing the weight vector to be too small, and again we end up with pretty bad looking performance. Okay, this will come back later. I will talk later about methods for setting this thing and other hyperparameters, but I want to emphasize even at this fairly early stage that getting it right is critical. Now it turns out that not only can we actually get an analytical solution for the regression case here, using the kernel trick, we can get something much nicer than just standard gradient descent in the case of classification as well. So, I talked about how the error function changes if we want to do classification, because we then need a different likelihood function. And in particular I suggested the use of the sigmoid. The function that I ended up with specifically the expression that I ended up with for the probability of the data given a particular weight vector was this one here. And if you've been doing the exercises, which I hope you have, you will have followed that derivation through a little bit further, and you will have found that the relevant error function to be minimized now is no longer the sum of squared errors, but it's the one at the end of the slide here. Okay, so now we're in the classification case with two-class classification, not the regression case, and this is the error function that we now want to minimize. Now we can't do it quite analytically at this point, but we can get something that tends to converge much quicker than just basic gradient descent. The reason for that is that in this case we can use the Newton-Raphson method. I hope you remember the Newton-Raphson method from an earlier course. I'm fairly sure it will have been in NST Maths. Well, it doesn't matter because I'm going to show you what it is now. If you want to know how and why it works, you can, of course, go and look that up. I'm just going to present it as a method for finding the stationary point of a function. But what we want to do now is find the w that minimizes this e of w. And the Newton-Raphson method gives us a recipe specifically for finding points at which functions are zero. Okay, and in one dimension it looks like this. Okay, it's still an iteration. It's just something that's a slightly different iteration from gradient descent, and it's going to tend to converge more quickly. Now that finds f of x equals 0, so if you want to use it to find the minimum of a function, you can just use it to find the point at which the derivative is 0, and that's a very minor modification. Okay, the main take-home message here is that in one dimension you're going to need both the first and second derivatives in order to apply this recurrence. Now, in many dimensions, it shouldn't come as a big shock that you end up with a very similar looking expression, but one that now involves vectors and matrices because we've gone into multiple dimensions. So now, if we want to use this in order to minimize e of w, the expression that we need looks like this. Now, in the one-dimensional case, we had the first derivative divided by the second derivative. Now, in the many-dimensional case, we have the first derivative again, and it's divided by the multidimensional version of the second derivative. Okay, in fact, the multidimensional version of the second derivative is called the Hessian, and it's been inverted here, so it's like dividing. And the Hessian is just a matrix of values that you get by taking the partial second derivative in all possible ways. So the ijth element of the Hessian matrix H is the second derivative of E, in this case, with respect to the ith and jth weight values. Okay? Now, all that actually leaves for us to do is to work out what the first and second derivatives are for this particular format of the error function e of w. Now that's not actually as tricky as it looks, okay? But we are getting into a little bit of sort of how can I describe this? What's going on here is basically a case of differentiating and being very careful to keep track of subscripts. Okay, there's going to be a lot of this, but it's not fundamentally any kind of particularly tricky derivation that we're doing. We start off with the expression for e of w as at the top of the slide. I'm going to simplify things and make theta equal 1. Okay, theta is the parameter that I put in the sigmoid that sets how steep it is. Okay, we can leave that out for now. It's not too critical at all. But I'm also going to use Z as a shorthand for the output of my classifier on a particular example. Okay, so Zi is the output that I'm getting from my classifier for the ith input vector x sub I. Now it should be straightforward to you. You all know how to differentiate. Okay, if you take the derivative of E of W with respect to the kth weight vector, well, the derivative goes through the sum. We're not worried about that. The only even remotely tricky thing here is that we're differentiating the log of, in fact, Zi here. So we get the 1 over Zi. And then it's a function of a function, so we need dzi with respect to the weight. And essentially it's the same thing for the rest. Okay? The situation for the rest of the expression is essentially the same. 1 minus yi doesn't depend on the weight, so just like y here, it stays as it is. We've got log 1 minus zi here, so we get 1 over 1 minus zi here, and we have a function of a function, so we need the derivative of zi with respect to wk. The rest of the slide is just rearrangement. Okay, all I've done is taken dzi by dwk out and rearranged what's left into a slightly tidier format. Okay, and I get this here. The only other thing that's really left to do is the derivative of zi. So, what does that look like? Well, the sigmoid has a nice property associated with it, which is that its derivative can be written in terms of itself. Okay, so dzi by dwk, again, it's just a function of a function, and we end up with z1 minus zi, okay, that comes from this expression here. And we just have to differentiate W transpose phi of xi with respect to the kth weight, and we've already done that a few times in fact, so it should be easy to see that we end up with this element here. And the final thing is just to collect those together for each individual weight. Okay, we have an expression for the derivative with respect to one weight, the kth one here, and we can collect everything together into a matrix vector format, and we end up with the expression at the bottom of the slide. You may need to sit down with a piece of paper and follow this through step by step. Okay, I strongly suggest you do. If you do that a couple of times, then manipulating this stuff becomes pretty much second nature. That gives us the first derivative. I leave again as an exercise. Okay, it's in the problem sheet, and you can do it for a supervision and discuss it with your supervisor, but it is left as an exercise because you do need to practice this stuff. The demonstration that the Hessian matrix has an ith jth element that looks like this. Okay, and that means that you can in fact write it as quite a nice matrix product, where Z is a diagonal matrix with elements that are kth element zk1 minus zk. If you're in any doubt at all about how to deal with matrix expressions like this, the way to do it, and I can't emphasize this enough, is just to write everything out in full and convince yourself that it works. Okay, so let me give a specific little example here. How are we going to deal with something like that expression where we have matrix transpose times a diagonal matrix times a matrix, and we want to convince ourselves that the elements do actually look as advertised? Well, okay, let's start with just the diagonal matrix times our matrix A here. That's going to look like D1, D2 down the diagonal. And I'm going to do this for the case where the matrices are square, although that's not strictly the case necessarily on the slide, but you can convince yourself that it still works out in the way that's being advertised here. The matrix A will then have elements A1, 1, 1, 2, A2, 1, A2, 2, and so on, all the way down to ANN. Well, this is just matrix multiplication, so what do we then end up with? Equals... Well, the first row on that D matrix only has one non-zero thing in it. So we're going to end up with just D1, A11. And D1, A12, and so on, all the way to D1, A1n. And then the second row of that diagonal matrix only has one non-zero thing in it. So we're going to end up with D2, A21, D2, A22, and so on. And the pattern is straightforward. Okay, well now we need to put a transpose in front of that. So what's that going to do? Let's cheat slightly here. Well, it's transposed. So this is going to be A11, A21, A31, and so on, because everything's been swapped. Okay, and now it's maybe slightly less friendly. Let's just take that and work out what one element in the resulting product looks like. Let's take this row and this column. So the element that we're going to be looking at is going to be the second row and the first column of the resulting matrix. And it's going to look like D1, A11, A12 plus D2, A21, A22 plus D3, A31, A32, and so on, which is going to look like a sum over K of dk AK1, AK2. Okay, so each element of the resulting product is going to look like that, and I think if you compare that to what's on the slide during the derivation of the Hessian, you'll see that everything matches up just fine. Now once you've got that, you can simply collect together the first and second derivatives that we've just derived, plug them into the Newton-Raphson expression, and that gives you something called the iteratively reweighted least squares algorithm, which can be used for training a classifier in this format when you've used basis functions to map things into a higher dimensional space. Okay, so that's actually quite a nice training algorithm. It tends to converge pretty quickly. You still have the provisos regarding being potentially a little careful about how you compute the inverse. There are numerical methods that can make that perfectly pain-free. Okay, but I'm just going to give you the expression. Now the final thing The final thing for me to say for this current piece of the course is that this is a visualization of what happens when you apply this learning algorithm to the data that I started off with, okay, to the non-linearly separable data at the beginning of this lecture. The surface that's at the top of this graph that extends between 0 and 1 on the z-axis is the actual function being computed by our classifier after I've trained it. Okay, it extends between 0 and 1 because it has a sigmoid on its output, and we take the point at which it's a half to be the point at which we're distinguishing between one class and the other. That's all then been projected down into the x1, x2 plane, which has the data in it, and you can see where the lines corresponding to a half are that act as the decision boundary in this case. Okay, that's just been obtained by applying iterative reweighted least squares to that specific bunch of data and then plotting what I got as a result. And similarly, when I showed you earlier the fact that you can divide this data in the three-dimensional space, this is the linear function that's computed by the same classifier. Okay, so in this case I've got the actual linear relationship but left it in 3 dimensions so that you can see that it does separate the data in 3 dimensionals as advertised.